All right, good afternoon, you guys. Today is Wednesday, May 13th. I know you guys are hearing it from all your teachers and stuff like that, but finish line's in sight. We've got 4 more assignments, including today's assignment. So just really hang tough. You guys especially, man, you guys are getting into some stuff that's really going to be good exposure stuff going into your freshman year of college if you're going to be taking a freshman Calc course, okay? So all this integration stuff, which is just the opposite of finding a derivative is finding the integral. This is all stuff that you spend just tons and tons of time doing in a college Calc course. So just your general exposure to this is really a big deal, okay? What we're going to look at is basically this. And before I get into the actual notes themselves, I want to mention what you've seen so far is integrating polynomials, okay? So integrating a polynomial is a relatively easy thing to do because you just integrate each individual term one at a time. What we're gonna get into now is integrating things that we can't turn into just polynomials, or we don't want to, okay? So what you're gonna see here, this first example that I have for you guys is this. We're gonna integrate or find the integral 3 times 3x minus 1 to the 4th, which with respect to x, okay? So again, that dx just means you're finding the derivative with respect to x. Now, here's the thing. We don't want to FOIL 3x minus 1 to the 4th power. There's got to be an easier way. There's got to be a shortcut. It's just like all the differentiation rules, right? You can differentiate anything if you can turn it into a polynomial, but there's the product rule, the quotient rule, the chain rule. There's all these rules for differentiation that make things easier. It's no different than what we're going to be spending our time doing with the remaining time we have together with integration. There are integration rules that we can use to integrate things that we don't want to try and FOIL out into a polynomial. Now, I'm going to show you the integration by substitution rule itself, but it's going to make a heck of a lot more sense to you if I can show you this first. Let me talk about this function right here, 3x minus 1 to the 5th power over 5. How would we differentiate that? What would be the derivative of this guy right here? So what we would do is we would use the chain rule. I mentioned that, right? The chain rule says if you have an expression raised to a power, you can follow the basic power rule. Bring the 5 out front. So basically, we would do this to the top. We would bring the 5 out front. 3x minus 1 stays the same. You drop the exponent down to a 4. So what you're going to see here is those 5s are going to cancel. And you're left with just the 3x minus 1 to the 4th power. But what does the chain rule say? Chain rule says when you do the power rule, you bring the 5 down, you take 1 off, you have to multiply this by the derivative of the inside. So what's the derivative of the inside? It is a 3. So here's your final derivative of that original thing. The derivative is 3 times 3x minus 1 to the 4th because you have to account for the derivative of the inside. Okay, so here's the rub. This integral that we're finding is this right here. It's the derivative of 3x minus 1 to the 5th over 5. Okay? So what I want to show you is this. If we're finding this, we should be able to work backwards from this up to the original function to find the actual integral. So we should be able to evaluate this. What I need you to see here is this. I'm going to show you the substitution rule, but what you have to remember is that the substitution rule is something that we're going to use so that we don't have to FOIL this expression out, but we have to remember that we have to account for the chain rule. So in this instance, what I want you to see here is this. 3x minus 1 is a function. Its derivative is 3. So you have a function and its derivative in the same integral that you're trying to work with. If that's the case, if you have this function and its derivative, what you can do is you can apply the basic power rule that we were applying the last 2 days. You can take 3x minus 1, raise its power up 1, so 4 goes to 5, and then put it also that 5 in the denominator. And of course, we have the benefit here of we know that that's the answer because this is what we started with when we differentiated to get down to here. So when we work in reverse, we know that that's what we should get to. So here's what I want you guys to see. you can take an expression 3x minus 1 to the 4th power, and you can do the basic power rule, which again says raise the 4 up to a 5, but then put the 5 in the denominator, and that's your answer. That's the integral, okay? That's the antiderivative of this. The only reason you can do that, though, is because the original problem itself had an expression and its derivative, okay? So what you're going to see today is this. The problems I'm going to give you have to be very specific in their setup. You have to have a function and its derivative both together in the integral in order to do that basic rule. Now, the substitution, I'll explain exactly where that comes from. The one other thing I do want to mention is this. Remember, this is the derivative, this is the original function. The symbol we use for finding a derivative is this prime symbol. When you're identifying or showing to me that you have now found the function or the original function found by doing the antiderivative, instead of writing a little prime mark here, we write a capital F of x equals 3x minus 1 to the 5th over 5. This means this is the original function. This is the antiderivative of something, okay? So instead of finding the derivative of that, we found the antiderivative. We denote antiderivatives with the capital F of x, okay? So here's the where substitution gets its name, I guess. We would say that if you want to do the antiderivative of any function u. So we a lot of times in calculus we use u as a means of substitution where u is not a number and u is not a single term. U is a actual entire expression. So it was the 3x minus 1 in this case. That's what u is. And I shouldn't have put the squared there. I should have put that through an nth power. U raised to the nth power. All right, so if you're going to integrate u to the nth power, the only way that's possible is if u's derivative is also in here. So how do we write the derivative of u? That's du dx. Again, this just stands for the derivative of u with respect to x. And then just like up here, we always have this dx at the end telling us what we're differentiating with respect to x is. So if you have an integral, u to the nth power, and you have u's derivative, the actual integral is just, you do the same thing that you always do. We do u to the n plus 1 power over that same thing, n plus 1 plus c. Okay? So it's called substitution because you're not actually taking a single term raised to a power, you're taking that whole expression and you're representing it with this u right here. Now, I know right now you guys are probably wrinkling your eyebrows just a little bit and you're wondering you're probably wondering just how lost you actually are. I think if we see a couple examples here, you're going to see that it's not too terribly bad because I have to give you very specifically set up problems, okay? So let me show you some examples of doing integration by substitution. So I want you to find this integral, meaning find the antiderivative of this expression, 2x plus 1 times x squared plus x with respect to x. Now, let's get the cat out of the bag right away. We could FOIL this together very easily. We could FOIL this apart, get a polynomial, and then integrate the polynomial the easy way. But here's what we want to recognize. X squared plus x is, or the derivative of this is 2x plus 1. So if we look at this, if we call this u, if we call x squared plus x our u up here, so we have u raised to the first power, and then right next to it we have its derivative. The derivative of x squared is 2x, the derivative of x is 1. So this x squared plus x is u, this is the derivative of u. So if you look, this is where substitution kind of gets its name. If you have a function raised to a power, that's our u, and you also have right next to it its derivative, all you have to do is focus on this. You do the same thing that we always do to integrate. You take whatever this is, you raise its exponent by 1, and then you put it over that same exponent. So take x squared plus x raise its exponent up to 2, and then put it over 2, and then slap a plus c on it, and you are done. Okay? So that was even quicker than foiling this out and finding its antiderivative that way. But again, the only reason that it worked this way, the only reason I could take x squared plus x and just simply bump its exponent up and write the exponent as the denominator of a fraction is because the original problem had u and its derivative. So this is kind of odd because sometimes people are like, well, I don't really get it. How do you go from having this x squared plus x and this whole other thing? Why do you only have to focus on this, raise its exponent up, and then put it over its denominator? It's because of the relationship between that and its derivative, okay? If, I don't know, we're gonna run out of time here if I over-explain this. I just need to show you some more examples here and get you comfortable with what we're doing, okay? So just bear with me here, okay? Let's find this antiderivative. 3x squared times the square root of x cubed minus 2 with respect to x. Okay, now here's one where we wouldn't have an alternative. We can't distribute 3x squared into a square root the way we can distribute and FOIL parentheses. So this one is made, again, only possible because if you look, this is x cubed minus 2 to the 1/2 power. But what is the derivative of x cubed minus 2? 3x squared minus 0. So you have a function and its derivative. If that's the case, you can integrate by just simply focusing on the function itself. X cubed minus 2, raise its power by 1, so 1 plus 1/2 is 3/2. Put that in the denominator, so it's over 3/2. But obviously we wouldn't leave our answer like that. We would do multiplying by the reciprocal, so this would be 2/3, and then x cubed minus 2 to the 3/2 power. Now, it doesn't really matter how we want to write this. If I want to write it as a function or as an actual equation, I can do this capital F of x. This is one where we probably have enough time to just show it. How would you differentiate this? You'd bring the 3/2 down in front. 3/2 and 2/3 would cross cancel. All of this would go away. The x cubed minus 2 would stay. You'd subtract 1 from the exponent. So there's my x cubed minus 2 to the 1/2 power in my derivative here. But then it's the chain rule. So not only would you bring the exponent down to cancel off the 2/3, you'd have to, at the end, multiply by the derivative of the inside, which is 3x squared. That's where that 3x squared comes from. So in this one, we can at least see it working. We can see that if this is the derivative of this, it actually checks out. But it's kind of strange. Let me show you at least 2 more examples. I apologize. I know yesterday and today the notes videos got kind of long, but I want to make sure that I give you enough information here that you can get this done. Negative 4x over 1 minus 2x squared squared. Let's integrate that, okay? So let's integrate it. Oh, you know what? I forgot to put my plus c on that last one. Here, we have 1 minus 2x squared on the bottom. The derivative of 1 minus 2x squared is negative 4x, right? So you have this and its derivative. So that means we can just focus on this. This would be 1 minus 2x squared. If I just rewrite this, it'd be 1 minus 2x squared to the negative 2 power if I move that up to the top with the negative 4x. So we can, again, because the original problem has this function and its derivative, we can move that to the top and just focus on the expression itself. So what do? We go 1 minus 2x squared. We raise its exponent by 1. So that would be negative 1. And then put it over negative 1. And then we just kind of clean things up a little bit. So the negative, essentially the negative 1 doesn't really matter. It just becomes a negative sign out front. Well, actually, I'm going to have to put that on top because this needs to move back to the bottom because it's got a negative exponent. So it's 1 minus 2x squared moves to the bottom. It becomes a positive 1, so I'm just going to drop the parentheses and then put my plus c there. Okay, so essentially I just moved that to the bottom. I had to fill the top with a 1, and I moved this negative sign out front. So I'm hoping I'm not totally losing you guys here. I think a clarification video is going to definitely be necessary tomorrow, but I also need to show you guys one other real quick thing here. Okay, let me show you one last example. And it should be pretty obvious when something like this happens, so hopefully it makes sense here. X cubed times 3x to the fourth plus 1 squared. Let's integrate that. Okay, so when we look at this, we have a function raised to the second power, but now I want you to see this. Unlike all these other ones where the derivative of the inside is also in there, the derivative of the inside here would be 12x cubed, not just x cubed, okay? So what we need to do is we need to basically account for that, okay? Is the chain rule is not gonna work perfectly here because, again, when we differentiate, when we find the derivative, there's gonna be a 12x cubed, we only have an x cubed. So we need to sort of essentially get rid of that 12. How do you get rid of a 12? You multiply it by its reciprocal. So if there's a case like this today where you don't actually have the exact derivative of the inside because you have the variable but you don't have the coefficient, just kind of account for that by getting rid of it or putting a 1/12 at the beginning of it. Okay, so I'm going to put a 1/12 at the beginning of my whole my whole integration here because, again, I have to account for the fact that there's going to be a 12 in the derivative. Okay, so at any rate, just put the 1/12 and then do your integration the way that we do it. Okay, so 1/12 times. What do we do with this? We go 3x to the fourth plus 1. Raise the exponent up by 1, so it goes from a 2 to a 3, but then put the 3 in there. So instead of it just being this, 3x to the fourth plus 1 cubed over 3, you have to multiply that by your 1/12, and so it becomes, make sure you guys can still see this here, it becomes 3x to the fourth plus 1 cubed over 36. And just to prove to you that this checks out, real quickly here, let's in our head kind of do our derivative. The derivative here would be the chain rule. You'd bring the 3 down front, like that. You take the 3x to the fourth plus 1, drop its exponent down to 2. You'd put it over, that 36. And then you'd have to multiply by the inside's derivative. What's the derivative of 3x to the fourth? That would be 12x cubed. So if we look here, 3 times 12 is 36. So 3, 12, and 36 cancel. You're left with x cubed, 3x to the fourth plus 1 squared. That's up here. That's what we started with. Again, that's why we had to put that 1/12 to account for the derivatives of the inside not being exact. All right. So again, I hope I didn't totally lose you guys. Hopefully with having the answers in the back of the book, you can kind of work your way, navigate this and get some level of comfortability with it. But again, I'll probably have a relatively long clarification video tomorrow just to make sure that we're all on the same page before we move on. All right, guys, do your best with it. Let me know what questions you specifically have, and we will go from there. Have a great day.